napot kívánok! Tisztelt egybegyűlt kollégák, érdeklődők! Szeretettel köszöntelek benneteket, önöket, hogy ezen a délutáni, kora nyári időpontban itt csatlakoztatok a mai délutáni programhoz. Rögtön átváltok angolra, de előtte még szeretném megköszönni, hogy személyesen eljöttetek, illetve köszönöm szépen Szabó Istvánnak, a Hunren szervezetnek, a hálózatnak, a stratégiai vezérigazgató helyettesének, hogy csatlakozott hozzánk. And let me change into English, and I would like to welcome Professor Mihály Benedikt, who came from the CERN, and he will speak about the future. I would like to say the near future, but if you allow me one joke, now I know why I would like to live until 120 years, because I would like to see all of the physical results which will come out from the next accelerator. So this will be the Future Circular Collider. Our speaker is the main organizer, main responsible person for the feasibility study of this new accelerator. Professor Benedikt, he obtained his PhD from the Vienna University of Technology, and he joined to the CERN Accelerator Operation Group in 1997. He became an expert on accelerator and high energy physics. On the other hand, he was volunteered and hired and asked and joined from 2008 until 2013 as a project leader to the design and construction of the accelerator for the Austrian carbon-ion cancer therapy. Maybe you know MedAustron. This is just in Wiener Neustadt, close to the border. So this was his main project, and now it is working perfectly. Every year, approximately 500, 600 people are cured there. So it is a very important facility. In the autumn of 2013, Professor Benedikt was appointed to study the future, so as a study leader, the Future Circular Collider, and how it can be established, how it can be accomplished. And he has a mandate to develop the conceptual design for this Energy Frontier Circular Collider, which will be the main facility of the CERN after the LHC era. This work is going well, and just right now, last 2 months, 3 months ago, it was a report, so it is in halfway. And this was a good opportunity and occasion to invite Professor Benedikt that if he can come here, and here in Hungary, where there is a very strong commitment to the direction of the CERN. Maybe you know that more than 100 people are working continuously, elder, senior, and many young people, to the CERN physics to show us what is the recent situation, how we can make the FCC. So I don't want to say more because the real stuff will come. Thank you very much for coming. After your talk, which is more than 50 minutes, there will be 3 shorter talks from the Hungarian side, that how the Hungarian experts, considering the recent experience and recent capacity, are thinking and joining to this challenge to build the next huge accelerator. Please, Professor Benedikt, the stage is with you.
Thank you very much, and good afternoon. So in my talk, I would like to present to you this Future Circular Collider study and its status of development, which was just reviewed by the CERN Council. And the talk is split into, let's say, 4 groups. In the first one, I would like to show you the scope of this future project. and a little bit about the background when this study was launched, why it was launched, the results at this intermediate review that we achieved. And then I would like to show you a little bit, or give you a little bit of the feeling of where we stand with the preparation of the implementation of the project in the region. Because it's just to show you that we are far beyond the point where this is just only a paper study, but it's now really becoming manifested in the region. And in the third part, I would like to talk a little bit about technological developments on the accelerator side, on the technical infrastructure side, on the integration of all these with the local infrastructure. And I will, in the end, say a few words about collaboration and how the study is organized. Now, we call the program an integrated program because it consists of two different colliders that form part of it. And clearly the concept behind is to prepare and build a science infrastructure for the 21st century that will remain at the absolute top level, providing best conditions for high-energy physics, accelerator-driven high-energy physics, until about the time 2100. So there are two machines in there. The stage one would be a lepton collider, which we call FCC-EE, and this machine would operate at and produce the heaviest particles of the standard model. So it will produce Z, W, Higgs, and T bar pairs. So in that sense, it's not just a Higgs factory, as was recommended by the last strategies, but also an electroweak factor with the Z and the W, and the top factory. And the design goal for this machine was clearly to produce highest possible luminosities at all these working points, to provide maximum statistic under the cleanest possible conditions. Stage two in the longer term would then be a hadron collider, on a functional principle and conceptually similar to the Large Hadron Collider that is operating at CERN now, but of course nearly an order of magnitude higher in terms of center of mass collision energy, and also an order of magnitude higher in luminosities. And this would be then continuation of physics at the energy frontier, not just proton-proton, but like the LHC, also ion-ion or proton-ion collisions. Now, when you look at the physics program, which I'm not covering here, is synergetic and complementary, of course, on the two machines. The whole infrastructure is designed in such a way that, of course, the tunnel, the surface, buildings, and so on can be reused or are used by both machines. To largest possible extent, also the existing CERN infrastructure is reused. Obviously, common civil engineering and so on. And from the timing point of view, the project is integrated with the CERN operation plan in such a way that it guarantees continuation of high-energy physics immediately or very close after the completion of the high-luminosity LHC program that is presently projected to stop in 2041. So below you see these three stages. We are now on the left side here in the design phase, integrating the project in the region, then construction of all the civil infrastructures and so on, and then first collider, and then in the second stage, the second collider. Now, if we look a little bit closer in the timeline, perhaps just looking at the lower left graphic here. So at this moment, we are in what we call a feasibility study that was launched in 2021 and that will run until March 2025. This study should give sufficient input for an update of the European strategy for particle physics that will be launched in summer 2025 and will run until summer 2026. In case of a positive recommendation of this European strategy update process, the CERN Council with other financing partners could then approve the project typically 1 year later, somewhere 27, beginning of 28. And this in turn would allow to start the civil construction process at the beginning of the 30s, around 2032. Civil construction would take about 8 years to be fully completed, afterwards followed by technical infrastructure installation and accelerator installation and, of course, detector installation. so that operation could start somewhere in the middle of the 2040s, by 2045. And also indicated here is 2041 as the presently foreseen stop of high luminosity LHC. Now, once the Lepton Collider goes into operation, the completion of what is envisaged at this moment as physics program takes about 15 years, so that by 2060, the Lepton Collider physics program would be accomplished and achieved, and then a typically 10-year turnover period from the Lepton Collider to the Hadron Collider, like it was the case from LEP machine to LHC machine, would then enable start of the stage 2 Hadron Collider from 2070 onwards. Now, before moving in more details into the feasibility study, just a very brief one slide on the history. We started the study in 2014, following or answering to a request of the 2013 update of the European Strategy for Particle Physics that said that CERN should undertake design studies for accelerator projects with emphasis on proton-proton and electron-positron high-energy frontier machines. So you note from this statement that there was no specific mention of circular or linear or whatever. So in this period, we launched a conceptual design study for the Future Circular Collider. In parallel, there was, of course, also study ongoing of the Compact Linear Collider project and other alternatives. Now, the four reports that you see here in pictures are the outcome of this first conceptual design study. So there's a volume on the physics, there's a volume on the Lepton Collider, a volume on the Hadron Collider, and there was even a volume on a Hadron Collider with higher energy in the LHC tunnel using higher field magnets, which we called the high energy LHC. So these four volumes, and of course also all the other studies that were pursued, went into the next European strategy update in 2019 and 2020. And then the request was different. The strategy asked that Europe, together with its international partners, should investigate technical and financial feasibility of a future Hadron Collider at CERN, with a center of mass energy of at least 100 TeV, and with an electron-positron Higgs and electroweak factory as a possible first stage, and this is exactly corresponding to the FCC program. So consequently, CERN launched just one design study to prove the feasibility of the future circular colliders. Now, this study was started in 2021, and here you see the main goals. These goals can be, let's say, grouped in three topics. First one is we should demonstrate that the infrastructure can be built, so feasibility of the tunnel, technically and also administratively. This means you have to consider where you put this infrastructure, where you want to have your access points from the surface to the tunnel. And this needs, of course, interaction with the local region. It needs interaction with France and Switzerland, which are both host states of CERN. And, of course, also at the smaller level with the individual villages and communalities that are concerned by the project. Second big group is our core competency. This is the design of the accelerators, the design of the experiments, detectors, and the R&D on all these technologies. And the third block in this feasibility study is to develop the financing concept, the financing model, and to develop the organization and governance models for the project during the construction phase, but also for the project in the operation phase, of course. And this feasibility study should be sufficiently detailed to allow a discussion by the European strategy and afterwards by the CERN Council on the realization of the project, and it should enable also a decision on the project. And we will deliver this report by March 25. Now, the CERN management, together with the CERN Council, wanted, of course, to have a clear vision of the advancement of the study before this final date, to understand already at an earlier stage the direction that we are taking. And therefore, they asked for a mid-term review, roughly in the middle of this feasibility study. So we started this review in 2023. It took the second half of the year, essentially, and it reflects the status at the beginning of 2023. And we had agreed with the CERN Council a certain number of deliverables that should be presented in a certain degree of detail, which was done. So there's a report available for the CERN community that has some 700 pages and that describes all the advancements on these 8 deliverables. This review process went very well, and there were no showstoppers on the technical side identified, which was confirmed by all the review committees. So there were 2 specific committees, a scientific advisory committee and the cost review panel. And then there were the CERN Council committees, so CERN's Scientific Policy Committee and the CERN Finance Committee that also reviewed the entire documentation and made recommendation to the CERN Council that completed the review at a special meeting in February this year. So this review, of course, encouraged us, and it brought us also recommendations from all these committees, which aim, of course, at providing the best possible outcome in about 1 year from now. So now, if I look now forward into the next steps on a larger scale, for the next, let's say, 12 months, clearly the goal is to complete this feasibility study. The technical work will have to be completed by the end of this year because we will need 2-3 months beginning of next year to do the editing, to homogenize between the different work pillars, and to create a nice and complete documentation. In this work, we are focusing, of course, on the recommendations that we got from the CERN Council, and we will do other stuff like development of a larger risk register, redo and improve the level of detail and degree of uncertainty of the cost estimate that comes, of course, with increased technical design detail. And we're also working with the CERN Council on the development of a funding model for the entire first stage of the project. So completing this work by the end of the year will allow us to complete the documentation for March 25. In parallel to this, we are working in very close cooperation with France and Switzerland on project definition with the host states, on the detailed development of the implementation of the surface sites, and I will have some slides on this later, and on other environmentally most relevant aspects for the realization of the project. Now, once this feasibility study is completed, we are already setting up now in terms of resources and also on the collaboration side for a sort of pre-technical design phase that would run from beginning or from spring 25 until the end of 27, where a project decision should be taken. The goal here is to provide to the CERN Council, that is the deciding body, more detailed input to enable a well-informed decision on the project. So this concerns, of course, the civil engineering, that is a major block in terms of cost and in terms of activity, but also all the technical design of the major components. And moving again further into the technical detail will allow us to give a better cost estimate. Then what we are also trying to do in this phase, we want to prepare for the civil engineering to be able to start as quickly as possible after a project decision. What does this mean? This means we need to be able to launch the detailed planning contract for civil engineering immediately as we know the project should go ahead. But this requires, of course, that you know the requirements of the accelerator and of the technical infrastructure on the building, on the tunnel, on the shafts, on all these civil engineering buildings. And this means we have to have, by the end of 27, a complete integration design of the major components of accelerator and all the technical infrastructure. And this is, of course, a huge task because this requires a lot of technical work, integration studies. Then we also need to prepare the authorization process in France and Switzerland, which requires obviously an environmental impact study and environmental impact analysis, and this will be launched in 2026 with external consultants. And of course, in parallel to this, more detailed implementation work with host states. Now, I would like to give you a feeling of where we stand with the local implementation. So, to come to an optimum solution, you have, in principle, 3 big players that you have to balance, or 3 big aspects that you have to balance. You have to find acceptability in the region for the project. This means everything that is visible on the surface needs to be acceptable, needs to be compatible with environmental aspects, with urbanistic aspects. It needs to be integrated with the existing highway, transport, road networks, with the existing railway networks, because you need transport, with the existing electricity grid, because you have to connect your 100-kilometer infrastructure to the electricity grid at a few points, with the existing water distribution systems, because you need cooling water, your facility, and so on and so forth. So this is one big block that you need to manage. The another big block is the construction of the tunnel. There you have to look for the underground situation, the geological composition, the risk that you have if you put yourself in one region or in another. And the third big block is, of course, the scientific performance. Yeah, because if you build your machine too small, you will not have the energy reach of the Hadron Collider. If you build it too small, with a too small radius of curvature, you will have too much synchrotron radiation. You will not be able to produce high luminosity with the Lepton Collider. So these things you have to balance. And we studied about 100 different variants, difference in circumference, difference in aspect ratio, difference in number of surface sites, and so on and so forth. And finally, this converged to a 91 or 90.7 kilometer ring with a four-fold symmetry. So each quarter is identical to the next of the 4 quarters. The arc segments are all identical, so there are 8 identical arc segments. And the arc segments are combined either by a long straight section, which is 2.1 kilometer and houses technical elements for the accelerator. And then following arc segments are combined by a 1.4 kilometer straight section that houses the experimental insertions. So experiments will be located here at 0 degree, at 90 degree, at 180 degree, and at 200, a bit difficult with this mouse, 270 degrees. And in between you have the technical straight sections. The total surface need is 40 hectares, so typically 5 hectares for each of the surface sites. So this is not too much different from the surface sites that we have today for the LHC. Because of course the equipment is also roughly the same. And of course an experiment on the LHC is not too different from an experiment on a FCC EE machine in the stage 1. So this is on the local implementation. Up to this point, we were working mainly on data that were already available with the host states, data of geological models that come from the universities that have geology departments in the region, from the geological institutes of France and Switzerland and so on. And the surface data came from the host states, from the administrative organizations of the regions, of the canton of Geneva and so on. Now, based on this, you optimize your location. Afterwards, you fix it. And then, of course, you have to go to the villages that are concerned, and you have to speak with the local population. And you start this, of course, with the interaction with the mayors of the villages concerned. In total, there are 41 villages under whose territory the FCC tunnel would pass. And 10 or 11 are particularly concerned because there you will find surface sites. Okay? So since about a year, we have launched this contact, and we are discussing with these people, and we have now reached consensus with all these surface site locations, except for one where the optimization process is still ongoing. But for the other 7, these are those marked in the light green on this plot. With all the others, we have identified the individual plots, so the cadastral surface plots and individual plots that we want to reserve for the surface sites. And this reservation process is now put in place by France and by Switzerland to guarantee the availability of these land plots for the project during the design phase and the decision period up until the start of the project. So this is, of course, key and essential, because it's absolutely not easy to find locations where you can implement such a large infrastructure. Now I move to the underground site. So here on this plot you see a cut of the tunnel with the 3D geological model. And there are a few interesting aspects here. We want to stay in this medium brown area that you see nearly all over the place. This is molasse rock. Molasse rock is a soft rock, is a sandstone type rock that has no karstic structures, so there are no unexpected holes or whatever that are delicate if you do the tunneling with a tunnel boring machine. And there is normally also no water inlays with high pressure on the water. So this means this is an ideal medium for tunneling fast, with low risk, with tunnel boring machines. Now, when you look in more detail, you see that the tunnel trace comes very close to other structures. Here, this is the crossing of the Lake Geneva. You see in blue the lake bed. Underneath the lake, there's moraine structure, and the moraine structure goes close to where the tunnel will be. Here again, there's moraine structures close to the tunnel. This is a location where the Arve River is crossing. And here on this side is the crossing of the Rhone River. And here on the lower side, you see the light gray area. This is the limestone structures of the Jura Mountain. Limestone structure of Jura Mountain caused problems during the LEP tunnel construction because of karst and because of water under high pressure. So we would like to avoid this. Now, to understand exactly these interfaces between the geological favored zone and the less favored zone, we are now doing high-risk area site investigations, how we call this process. So we will do about 28 to 30 drillings from the surface down to the tunnel level, exactly on the critical locations. You see here, for example, this is the Lake Geneva. This is the Jura Mountain on this side here. Here on this side, you have the Arve crossing with a couple of drillings, and so on and so forth. In parallel to these drillings that go from the surface to the tunnel or some 20, 30 meters below, we also do seismological investigations. So with a vibrocam that sends out waves, and you measure the reflection time, and the individual interfaces lead to different reflection times, and then you can develop a large 3D model of the underground based on these seismological investigations, and you calibrate it precisely with your drillings. And then you end up with a very good model, and this model will allow us to put the tunnel vertically at its final position and to also decide on the inclination of the tunnel. Now this work, we are preparing this since more than a year, and this work will now start. All the contracts have now been signed. It will start in June 24. And of course, this is a work that will be visible in the whole region, so it needs the exchange with the local population and the acceptance already at this stage. Moving further to the underground design. So we have by now developed models, 3D models of all the underground structures at a level of detail that allows us to quantify, to first of all decide the construction technique and to quantify the material needs. So you can do a bill of quantities for everything that you need to construct a tunnel, and this allows you, of course, to do a relatively precise cost estimate, which is simply calibrated then by the equivalent experience from tunnels that were recently constructed in France and Switzerland. For example, Alp traversal tunnels, Gotthard, Brenner tunnels, and so on. And very similar for the surface buildings, we have one generic design for an experimental site, so all the buildings that we foresee on an experimental site, and we have one generic design for a technical surface site, all the technical buildings. And again, we have bills of quantities that we gave to local construction company that is specialized in industrial buildings in the region, and they made a cost estimate based on their most recent projects. So this means we have a good confidence in these numbers of these cost estimates. Then, speaking a little bit into the direction of environmental aspects, when we do the excavation of the tunnel, so the excavated volume in the tunnel is 6 million cubic meters. And when the material comes out of the tunnel, it will expand, of course, because it's no longer compact rock. And then it corresponds to some 8.3 million cubic meters of excavation material. Now, of course, this comes not out on one place. It comes out on the place where you put your tunnel boring machine, because the machine drills and the stuff comes out where you start the machine. And So you have to deal typically with about 1 million cubic meter on each point where you launch a tunnel boring machine. And a big topic is, of course, reusing of this material. The problem is that the molasse is not a stable rock, yeah? So you cannot use it in like a granite pieces or something like this, because it just dissociates in some sense. It's not stable. But of course, you can use it like a soil. The only problem is it is sterile when it comes out of the ground. So now we have a project. This is, in fact, the first experiment, FCC-related experiment. It's taking place on the LHC 0.5 on a field in front of the CMS site. You can see here the layout. And there are about 18 test fields that are made up. We are using the molasse material that came out of the high luminosity LHC civil engineering construction in the last 2 years. And we are, with several university partners and industrial partners, we are working on processes to transform the sterile molasse into a fertile soil that you can afterwards use to do land filling and to cover the land filling with a fertile couche of soil. And so in this way you can transform today agriculturally unusable land into useful land for agricultural purpose. And this, of course, allows you then to even compensate, not just to get rid of your excavation material, it also allows you to compensate for the land use for the surface sites by creation of new agriculturally interesting land. So this is part of the project. And of course, a side effect of this is, if this project is successful and demonstrates how you can reuse molasse, it will be, of course, it needs an approval by the countries, by the host states. So if we get this approval, the technology can be applied to any tunnel project in Europe or elsewhere where molasse is the main material. And these tunnel projects are frequent. And so there is, again, if you want, a socioeconomic component of large scale integrated here. Now moving from the tunnel to the technical infrastructure. Looking here in this slide at transport and at electricity. Of course, for such a huge project, transport is a major issue. Not just for the construction, also, of course, for the operation phase, but in particular for the construction phase. So we have taken this into account, and we could position, finally, the project in such a way that on 4 main points where we will have major excavation taking place, on point D, on point G, on point J, we have a very close highway connection. Very close means within a kilometer, with an existing highway access station. So you just need to bridge the place from your surface site to the existing highway access zone. And this is, of course, very efficient and, again, helps us with the acceptability of the project. And in total, to access all the 8 surface sites in an adequate way for any kind of transport and work, we will just have to build about 4 kilometers of road at the departmental road level. Yeah. I will not go into detail on the railway connections, where we've also optimized in a way that we can access closely to 2 existing railway lines. On the right side of this picture, you see the electrical connection concept. So the FCC-EE phase 1 machine has a maximum peak power consumption at the TT bar working point, which is the highest energy working point of 380 megawatt. So what we foresee here is 3 connections to have a certain redundancy, each rated 200 megawatt. So a total power rating of the connection side, 600 megawatt, with a maximum consumption of 385. Point A, which is on the top of the graphic, is very close to the LHC 0.8, so very close to the LHC-B experiment, just adjacent, touching it. Yeah? And this point will be served by 200 megawatt that come directly from the existing CERN 200 megawatt connection with the EDF RTE network from the CERN Prevesin site, for those that know the CERN infrastructure. And then we need 2 new points, 2 new connections. And you can see this here. There is one 400 kilovolt line that traversing south of the Lake Geneva. And we are very close with 2 surface sites to this line. And this allows us to realize a connection at the point H, to the 400 kilovolt line, and again a connection to the point D on this side, so that we have a very nice balanced, let's say, and redundant network. These studies are not just done by us. We have done them with the French network operator. This is the RTE company, which is obviously a state-owned company, and they have confirmed, first of all, that they can do these connections. There's no significant impact if we take the 3 times 200 megawatt on this existing grid network. So there's no need on their side to reinforce, renovate, or change, or adjust the grid network. And this is, of course, for us a very positive message, because as you know nowadays, if you have to build or rebuild high voltage terrestrial lines, this is something which is always a delicate process, but this is not needed here. And of course, this supply concept is already covering also any needs for the stage 2 accelerator for the Hadron Collider. Now I move towards the machine side and to the integration of the new infrastructure with the CERN infrastructure. So if you look here on the right side, this is the overall picture. You see the LHC, this circle here, and the FCC, which is the lower circle below, and you see the SPS, and the red square is zoomed in on that side here. So you have on the top here, you have the LINAC. This is the particle production complex, so electrons and positrons. This will be located on the surface on the CERN Prevey-CERN site, roughly behind the SPS North area, so to the east side from the SPS North area. And then from that point, the beam is accelerated to some 20 GeV by high energy LINAC, and then it moves downwards to the SPS. It touches the SPS tunnel close to the point 4. This is done on purpose, of course, to also have the possibility to bring this beam into the SPS if should there be any reason to do an experiment that would involve acceleration or whatever via the SPS tunnel. And from that point, the beam moves further down to the level of the FCC and is then injected clockwise and via a U-turn and the antiparticles anti-clockwise into the FCC direction. Now, this choice of being close to the SPS and having a transfer line that has the same bending radius as the SPS machine also allows us, in principle, for the stage 2, for the Hadron Collider, to use possibly a superconducting machine in the SPS tunnel at much higher energy than the SPS today as injector for the future Hadron Collider, and to reuse then the already built transfer line. Now a look on the injector complex. So this is let's say it's a rather classical lepton production complex. There are some electron sources, the electron LINAC. This is all in the few GeV range. Then at somewhere on the few GeV, perhaps 6 GeV, there is a positron target. So the electron beam hits the positron target. There's a positron production. There's a positron capture system that captures the positrons, pre-acceleration of the positrons. Then a damping ring to improve the beam quality of these positrons. And then the positrons are fed back into the common LINAC, accelerated, and are sent to the high-energy LINAC. And if you have only the electrons, of course, they just go through and they go directly to the high-energy LINAC. Now, positron target and production is always a topic that, it's a topic that is not done so frequently these days. So we have a larger setup with partners that is located at the Paul Scherrer Institute in Switzerland, where we do a positron production experiment. As you know, there's the Swissfell free electron laser LINAC operating at the Paul Scherrer Institute, providing 6 GeV electrons. And with this LINAC, we got a beamline there, and we will put this positron target that you see here on the lower part that is produced at this moment at PSI, and the capture structure is located in one of the experimental zones of this Swissfell. And we will have the opportunity to test and verify production efficiency at different energies, because we can vary the energy from the LINAC, so that we know by 25, 26 definitively that the concept works and fulfills all specifications. And the target design and all this was done in a way that is directly scalable to the full power target for the FCC-EE. Now this is just for your reference and for completeness, the table of parameters. I will not go through the details here. Just to mention one thing that is decisive for the dimensioning of the machine and for the key technologies, we allow in the lepton collider the beams to lose 50 megawatts in form of synchrotron radiation at every of the 4 different energies. Yeah. Since the synchrotron radiation depends to the force power of the kinetic energy, we can have much more beam circulating in the machine at low energy, so at the Z pole, than at high energy, and this of course transforms into much higher luminosities at the Z than at the TT bar. It also transforms into completely different requirements for the radio frequency system at these working points, because the radio frequency system has to bring back this 50 megawatt onto the beam. And this means radio frequency and the efficiency of the radio frequency system is a key technology and a key important object in this machine. And we need completely different configuration for the different working points. So if you look at the left and right, these are 2 different operation sequences. In one case, physics is starting with the Z pole. In the other case, physics is starting at the Higgs. This is a decision that can be taken at a later stage of the project. You just have to configure your machine or your RF systems accordingly to be able to run at one or the other beam energy. The important thing here on this, or the important message is, this is a machine that will not be static like the LHC. We put the LHC in place, and the LHC is then operating for years in this roughly the same configuration. Now we make a luminosity upgrade, but then it will run again in the same configuration. This machine will have a quasi-permanent change, because whenever you go from one working point to the next, you modify substantially the RF system. You can bring in latest technology, new power sources on the RF. So there is a long-term parallel RF R&D program in all aspects with the lifetime and the evolution of the machine. Yeah. And of course, perhaps similar aspects will need to be taken into account on the detector side, since there is a different physics that will be seen in the different phases. Now a few slides on R&D activities to give you an impression what is being done and what we are looking at. So clearly radio frequency is absolute key issue. 100 megawatt of synchrotron radiation needs to be compensated. When you take into account the efficiency of the radio frequency system, this translates into 200 megawatt of electrical power. So whatever you can do to improve the efficiency of the RF production or of the cavity systems is extremely useful. And so there are lots of efforts that are going into this domain. I will not go further into detail here, but there are 2 different cavity types. One is copper cavities that are coated with niobium, or possibly with other superconducting materials, A15, niobium 13, but this is still in the R&D phase. And on the higher frequency side, 800 megahertz, there are bulk niobium cavities. There's a lot of R&D on the RF production. In the middle, you see new designs of klystrons to improve klystron efficiency by 20–30% compared to what is presently achieved. There's also, of course, a lot of activity on the machine designs, on the magnetic design and on the lattice design, so how you configure your magnetic elements around the circumference, how you can achieve the best possible final focus to maximize luminosities in certain conditions. And of course, important here is to design something that is good for operation, good in the sense that it is tolerant against field errors, against positioning errors. So the alignment of a 90-kilometer accelerator is obviously a non-trivial topic. And the more tolerant your lattice design is against these aspects, the better and the more stable and the more efficient will, of course, be the operation phase. So this is key things that are permanently improved. Looking a bit more into the engineering side, you have to see that 80 kilometers of this machine consists of arc. And the arc is nothing else than a repetitive structure. You design your arc cell. The smallest unit is a half cell from the accelerator physics point of view. And this half cell is quasi repeated then for 80 kilometers. The half cell has a length of 25 meters. So this means it is absolutely worthwhile to build at the earliest possible stage yourself a model of this half cell. And whatever you develop, you put it into this one-to-one scale model to understand transport, positioning, maintenance, accessibility, integration aspects, and of course all this keeping in mind that you want to industrialize the production as much as possible. So you have to take all this into account. So we are building, or we are now preparing in one CERN hall on the Marin side, we want to build a tunnel segment of 25-meter length to have really the full, let's say, geometrical conditions, and then we will install in there a mock-up of 25 meters of the arc to have a one-to-one model in the end with all the cables, with all the water piping, with all these elements to optimize really this structure in terms of cost, operationability, and maintainability. Another topic coming back again to the sustainability is the question of powering of the magnets, magnet design. So we have a lepton collider in the tunnel with two vacuum systems. If you remember, the LEP machine had a single vacuum chamber, and the electrons and the positrons were circulating in the same vacuum chamber. Now, having both particles in the same vacuum chamber meant that you have to avoid that they see each other all the time. Sorry. And this means that you had to avoid filling the ring completely with punches. And this means that you have a lower efficiency in terms of luminosity, of course, because you're not doing the maximum. That's why we have two separated vacuum chambers. But two separated vacuum chambers means we can fill the machine completely. But of course, you have to have two magnetic channels, one for each vacuum system. And here you see designs of magnets that can supply magnetic field for both vacuum systems while having only the powering needs of a single magnet. Yeah? So this means you gain a factor 2 compared to a classical solution where you had two independent magnets. And this is done by these dual aperture systems. And the magnet design is even strongly simplified. If you look at the right side, so this is two quadrupole magnets. One quadrupole aperture here, the other one here. You see the hyperbolic shapes of the quadrupole apertures here. And there's one coil that closes on the top and the second coil that closes from left to right on the bottom. And the normal quadrupole magnet would have 4 coil pairs around each of the 4 poles. Yeah? So this is also technically much easier, from the production much easier, and it is energy efficient by a factor 2 compared to 2 independent quadrupoles. Another topic that's also interesting is considering to replace these quadrupoles in the arc that are the main consumers. The quadrupoles and sextupoles along these 80 kilometers of arc are the main electricity consumers, not the dipoles that bend the particles. It's the quadrupoles and sextupoles. This thing counts for about 50 megawatt at the TT bar operation point. So there is R&D to replace quadrupoles and sextupoles by low-field superconducting magnets. Yeah, you can imagine to use high-temperature superconductors in a low-field application, so typically field at the coil of 1 to 2 Tesla, not higher. This means you can operate these high-temperature superconductors at temperature level up to 40 Kelvin, which makes it thermodynamically interesting, because you don't need so much energy to cool down to 4.2 or 1.9 Kelvin as we need in the LHC systems. And this is, again, an R&D that's ongoing, and where we will have first results in 1 to 2 years to see if this is a way to be pursued further. And then looking a little bit more towards the interaction point, we have also designed, again, using a special design concept, which is called Candid Cosine Theta technology, the final focus quadrupole magnet. This is a picture on the left here. So there's a prototype that was tested cold at CERN and that performed exactly to specifications, or exactly confirming the theoretical expectations. And with a partner in Italy, with INFN, in the Frascati laboratory, we are now setting up a mock-up of the machine detector interface, which is obviously also a very critical region, because you have this most inner detector chamber, and then you have the coupling to the cryostats that contain the final focus element, the compensation solenoids, and all this magnetic setup. That is, of course, in the lepton collider all integrated inside the detector, because the L star, so the distance from the collision point to the first magnetic element, to the quadrupole, is about 2 meters here. So contrary to the LHC, where you have all the magnetic final focus far away from the detector, here we are in the middle of the detector, and this makes, of course, comes with its own challenges and problems. Now I move to the hard-on machine. Here again, the parameters. So I said the goal in terms of collision energy is on the level of 100 TeV, center of mass. Here we quote a range, and the range is quoted for one main reason. The key technology for the hard-on collider is the high-field superconducting magnets. The goal is to reach an improvement with respect to LHC by a factor 2, so to go from 8 Tesla to 16 Tesla, plus minus some margin. And there are two technologies that are available to go this direction. This is either niobium-3 like it is used for the high luminosity LHC upgrade, but that one is definitively limited to 16 Tesla. And the second technology is high-temperature superconductors, which are far less developed in terms of application for accelerators than the niobium-3, but which may have completely different potential, because they are not limited to 16 Tesla. They could probably go to higher field. One could operate these magnets also at probably somewhat higher temperature, to the 10 or 20 Kelvin range. So there are different aspects that need to be taken into account. And the main point here is we see that we have about the 25 to 30 years R&D program in front of us to develop the magnet solution that would then be industrialized for the construction of this accelerator. And this makes it impossible to do a serious prediction at this moment of which technology you should be really going for. So we have to go here in steps and see with the advancement of the R&D which direction should finally be taken. So this means for the hard-on collider at this moment, our really key issues and main focus is on the optics design, because of course we have to have a solution that fits perfectly with the tunnel and with the lepton collider. And the second big activity is magnet-related, all sorts of magnets. Of course, the high-field cryomagnet system is one of the main blocks. So here is summarized what I just said. But then there are also other aspects, and I have here 2 slides. I think you will hear more details in one of the presentations afterwards. But I thought I should mention this here, because this is a collaboration that we launched during the conceptual design phase already in the 2015 to 2019 era with the Wigner to design, produce and test a new concept for septum magnets. So a septum magnet is the thing that you need to bring a beam either into the accelerator onto the orbit, or to take out a beam from the accelerator. Yeah? So how does this work? Yeah, you may have a beam that is circulating, and then you want to add more bunches into this segment. This means you come from outside, and you have to bend the beam from the outside close to the orbit on which it should go ultimately. And this, of course, you do with a magnetic element. Now, if we go with this hard-on collider to very high energies on the injection and on the extraction side, we need very high fields. And if we can't have high fields, we need very long distance, which we don't have. Yeah, so we want high fields. We want superconducting septum magnets. It's called septum magnet, this object that should take very little space, but should provide very high field on one side, so that the injected or extracted beam goes in, and it should have no field on the other side to have zero perturbance of the circulating beam. Yeah? And all this at minimum space. So this calls for a superconducting magnet, yeah? Because then you can go to 2, 3, 4 Tesla. So that's one thing. The second question is, how do you organize the field-free region? Yeah? With the superconducting magnet, you can easily create a field, but you need a field with zero you need a region with zero field. And this is shown on this SUSHI, superconducting shield septum. That is the development with Wigner that you can see here on the bottom. So you have your external stuff here. This is the magnet that produces a dipolar field, a high field. And in this, you bring, if you want, a superconducting material. This is the blue thing here. And you bring the superconducting material into this magnet before you power the magnet. And then you make the superconducting material superconducting. So when you switch on your external magnet, eddy currents will start flowing on the surface of the superconducting material that will prevent forming of a field inside. It's nothing else than an eddy current that will start flowing. And this eddy current will keep the inner region field-free. And if you can build this insert object in a good way with very small material between here and here, then you have managed what you wanted to do. You create a very high field on one side and zero field on the other side. And so this was a very successful collaboration. And here you see stages of the construction of the magnet. This is a canted cosine theta magnet on the left here, special coil geometry. Then there's impregnation. Magnet was built. There are different insert materials that were considered to create this field-free region on the inside. And this magnet was successfully tested a year ago in Sweden at the Freja test facility. Here now to complete the picture on accelerators technology, just for your info, the cross sections of the tunnel with the two colliders installed. Now the colliders are always on the left half of the picture. The right is just an indication of the space needed for the transport and an escape lane for a person that is involved in the work. So when the work and installation is finished, the right side is empty, and you have the machines on the left side. Lepton collider is this object here. On top, you have a booster. It's a third machine in the tunnel, 100 kilometers long. That is the machine that is permanently injecting, like in a light source, in synchrotron light sources. The light source is always running, and a booster machine is permanently feeding new beam into the machine. And this is the same case here. The collider is always in collision mode, 24 hours, and the booster machine will refill intensity into the collider quasi-permanently to keep and reach highest luminosities all the time. And on the right, you see the Hadron Collider is the magnet system with the two magnetic channels, and this is the cryogenic supply line. So this brings me to the end of the presentation with a slide on the collaboration. At this moment, there are 150 members. So the whole study was set up from the very beginning as a global collaboration. The goal is to involve a maximum number of partners from academia and, of course, also research institutes from all over the world to create a network that brings together best knowledge on the various and on the large amount of topics that we have to cover. And, of course, this network also provides, from a very early stage onwards, the possibility to prepare for in-kind contributions, for individual contributions that can be optimally managed with low risk due to the involvement of partners in the design, conception, and construction of the contributions. And this, I think, is key, and this is underlying principle for the collaboration here. Yeah? And this, I have to say, I would like to thank at this stage Wigner, also all other participants, of course, in this process and in the study, because without this collaboration, we could have never reached the level of detail, the degree of completeness that we got. And this was also, that's why I put this phrase here, recognized by the CERN Council in the review that congratulated explicitly the team and all the teams and all the partners involved in the study for the results that were presented in the midterm review. Now, progress on the international higher level political collaboration side is just 2 weeks ago. So there was a joint statement signed between the US and CERN that is, for such an early stage, I would say rather explicit. When you look here at the lower part, should the CERN member states determine the FCC is likely to be CERN's next world leading research facility, The United States intends to collaborate on its construction and physics exploitation subject to appropriate domestic approvals. So this, I think, is a very, very strong and massive signal from the US on the willingness to contribute here in a substantial way. Yeah. Also on the CERN side, in terms of outreach, we had the first largest scale public information event 2 weeks ago in the Science Gateway with 400 people present, 200 online. This thing was intended really to give to the public in the region the information on the project, to have a discussion with the public. It involved, and we invited, of course, also critical non-governmental organizations that question the energy consumption, the land consumption, other aspects. So it was completely open. It was the first in a series of public meetings that is going on. And this brings me to the summary. So we have completed not just the first, but I would say a large part of the feasibility study by now. We have defined and fixed this placement, which is now fully supported by the host states and by the local entities that are concerned. We have this dialogue with the region ongoing. The study itself is on track. All this was just made possible clearly because of this really efficient and good collaboration with all the participating institutes, universities, and of course also with the host states. Next milestone for us is to complete the study in 2025 and then move into the European strategy update. And in parallel, we will run this pre-TDR phase so that with a possible project approval by 27-28, we could immediately go into the civil engineering design and then start construction by 31. And this plan here is compatible with starting the facility in 2045, but of course only if resources are available for these preparatory phases and only if a decision is taken timely. Yeah? Because also clearly should say that the schedule as such is not, there's no way to compress the civil engineering construction phase. Yeah? It's determined by digging a shaft and running a tunnel boring machine along a tunnel. And that you cannot speed up. There's no obvious stuff. So let me finish just with this announcement. There's the FCC week, which is our yearly conference week. This time we go to the US to foster even more the US collaboration and to invite, of course, in particular the US physics community to fully join the program. It will also be, of course, via Zoom webinar. So I would be pleased, of course, to welcome whoever can come and would like to join in San Francisco, but if you cannot go there, you are most welcome to join via the Zoom context. But I should say at this stage for next year, I count on you because next year the FCC week will take place in Vienna, and that the distance should be short enough. So I hope to see many of you in Vienna next year. Thank you very much.
Thank you, Professor Benedikt. And I think usually after this presentation, we didn't used to have questions, but Professor Benedikt will be here in the break for a few minutes, and after that he will go to the airport. So please use the break to approach him and ask him. So thank you very much. And now we have the 3 talk from the Hungarian part. I would like to ask Zoltán Trócsányi first, that you will speak about the physics potential. You have about 20 minutes, do I remember well? I think.
Yes.
Yes. You can use this mic here.
Okay.
So please, the stage is yours.
Thank you very much. So welcome to this session. Good afternoon. After this fascinating demonstration that the feasibility study is actually moving on at full speed, I would like to demonstrate that this machine is worth of being built because the physics potential is vast. In fact, I am not an expert on it, but this is a a conceptual design report mentioned in the previous talk appeared 5 years ago, from where I have taken most of the information, which you will see today. And this is 400 pages. So obviously, I'm not going to present and summarize 400 pages. I will essentially select some cards and show it to you. But you can certainly study it yourself if you are interested. I'm not yet an expert, but I may become by the start of the FCC, when I still will not be exactly 100-year-old. So before we start, I think we should summarize what we learned from the previous colliders, especially the LHC, but also the LEP and SLAC and Tevatron colliders. And I summarize this in a few sentences. First of all, we have discovered the Higgs boson, and we have started the exploration of electroweak symmetry breaking, which is a very peculiar phenomenon because we know it is a symmetry of nature, although we cannot see it. Then we also know that there is a spectacular agreement between the standard model theory, which is based on the electroweak symmetry breaking, and experiment. In fact, we saw it this morning that almost all measurements agree perfectly. The signals of new physics, of which we are all very much interested in, around the TeV scale, TeV scale, are at best elusive, or in short, we haven't seen any new physics signals. There are certain anomalies, but no proven new physics yet. At least from colliders, because from other experiments we know that there must be new physics, which we don't know of yet. And there is accelerator and detector performances of the past and present colliders, which are much better than they had been anticipated at the time of design. So all that you heard here is very ambitious, but you can be quite optimistic that by the time they will be built, the machines and detectors will perform much better than described here. And finally, as a theorist, I would like to convey the message from the theoretical viewpoint is that advancement in precision of theory gives a good inspiration to perform ever-improving precision measurements. And the first point I would like to make is that these machines, FCCE, FCCHH, will be primarily precision machines. In order to prove or demonstrate this, I want to focus on the Higgs couplings. So here you see on the right the branching ratios of Higgs decays into different final state channels, BB bar, tau plus tau minus, gluon, CC bar, quarks, photon, etc. And the main channels, massive vector bosons and TT bar, as a function of the hypothetical Higgs mass. Of course, by today, we know that the Higgs is 125, and this is the line which shows that point in the phase space. And from this picture, we see that nature was very kind to us. Kind because this Higgs mass means that we can observe many different decay channels with measurable probabilities. And from that, we can extract the many different Higgs couplings to the various particles. And this is an ongoing project at the LHC today. Now, I would like to demonstrate that how this total Higgs width and couplings can be measured at the FCCEE. Typically, we call the electron-positron colliders as precision machines. And here you see on the left the high luminosity LHC results. If there is a missing bar, then it is the standard model value, which has no uncertainty. These are the relative uncertainties that you can achieve, predicted relative uncertainties at different machines like FCCEE at 240 GeV. And then you can add the FCCE at higher energy. And then you can add the high luminosity LHC, which is, as we learned, going to operate for a long period. And there is also a bar for the ion collider, so the electron-proton collider. And you see that there will be a significant improvement in the relative precision of these various couplings. This is the coupling to the Z bosons, this is the coupling to the W pair, and this is the coupling to the photon, which is, by the way, massless, but via quantum corrections, the Higgs can also decay into 2 photons. On the right-hand side, I show the same couplings, the fermion pairs, and you see that the BB bar, which is the main decay channel, will improve significantly. The CC bar also, the tau also, and the mu will be measurable with a quite nice precision. Now, these couplings are important in order to prove that the Higgs boson that we discover is indeed the standard model Higgs boson. Or if you find a deviation beyond these uncertainties, then you can be sure that there is new physics behind. Here I add on the FCC modes also in the proton-proton collision mode. So that is the final bar. And these are the target relative uncertainties. This is 1%. So you see that all these couplings will be measured with better than 1% uncertainty, which is amazing in high-energy particle physics. I remember when I was young, when we talked about uncertainties, we always mentioned roughly an order of magnitude. So the 100% uncertainty. There are, of course, many other parameters and observable quantities in the standard model, which are not Lagrangian parameters, but equally important, like the masses and width of the Z boson, or the Weinberg angle, or the strong coupling, which can be measured at the SCCEE. This is the present uncertainty. This is kiloelectron volt. So that's why we have these very large numbers, and this is the present uncertainty. And you see what is the forecast uncertainty at the FCC. So it's almost 2 orders of magnitude, 50 times better precision, which is quite astonishing. And of course, when you reach such an uncertainty, then you will already start seeing probably problems with the standard model. These are similar quantities which can be measured: forward, backward asymmetry, or the W boson mass and width, the number of effective neutrinos below 50 GeV mass, and so on. The TTZ coupling will be measured with significantly better precision than we can measure it today. So the bottom line that you can take home, that at least an order of magnitude decrease in uncertainties with respect to the Large Electron-Positron Collider or the Large Hadron Collider. With this precision, we can explore indirectly the up to the 100 TeV energy scale. And with indirect results on the Higgs couplings, as I demonstrated, with correlated properties of W, Z, and Higgs bosons, and quarks and leptons. Also, significant improved precision on electroweak precision observables. We may perhaps discover that the standard model is not so good after all. It doesn't fit so well as we think today. Or we can further discover things which are hinted as anomalies at the LHC, like violation of flavor conservation and universality. But beyond the precision, the FCC can constrain cosmology or serve many other new results. We know that matter and antimatter are not in equal amount in the universe, because we are built of matter and we are here. And the major theoretical explanation, or the folklore, requires sufficiently strong first-order electroweak symmetry breaking. I mentioned at the beginning that electroweak symmetry is very peculiar. We know it exists, but we cannot see it, so it is broken. And it has to be sufficiently strong first order for baryon asymmetry. And we also need large CP violation. And these are absent in the standard model. So we have to go beyond the standard model, and they can be explained probably by beyond standard model physics. Now, testing CP violation exhaustively is beyond the reach of FCC, but testing phase transitions for specific, especially for specific simple models, is possible. And an example I would like to give is the very popular, because very simple extension, a singlet scalar added to the standard model particle spectrum, which can have a strong first-order electroweak phase transition in the parameter space where if it happens, the scalar can be explored exclusively. This is the mass of the second scalar, exclusively explored with the FCC-HH at 100 TeV with different luminosities. At the high luminosity LHC, it will be explored maybe in the smaller energy range. The dashed line means the 5 sigma discovery limit. Now, if such a scalar exists, then we can study its couplings to the Z boson, and we can its effect on the Higgs boson coupling to the Z boson, and its effect on the triple Higgs coupling. And if you make a scatter plot where the strong electroweak phase transition is possible, then you will find this region, and you see that this region is almost exclusively explored by the FCC-EE and the FCC-HH, so on the right-hand side and up. The current limit which is studied is in this region. FCC may discover new particles, many new particles. I will only mention one, perhaps a new gauge boson. This is a new Z prime, a new 1Z gauge boson, which is a massive gauge boson, so it will mix with the current Z massive gauge boson. And this, here you can see the current exclusion limits, and this is how this exclusion limit will be extended by the high luminosity LHC, and this is how it will be extended by the FCC-PP. I don't want to go to dark matter. There are many candidates for dark matter, and they are the weakly interacting massive particles are very popular candidates, and most of them can be exclusively studied. Another thing which is probably can explore is the feebly coupled particles in the 5 to 100 GeV mass range, such as right-handed neutrino, which many of us believe must exist. These are the exclusion regions. So this is the 100 GeV line that we can explore. So in summary, we may say that the precision of known physics will improve tremendously. We can explore the scalar sector almost completely. It will serve as a flavor factory, and we can test the CKM matrix and CP violation and flavor university, and we can search for new physics at these machines. So be prepared. Thank you.
Thank you very much, Zoltán, for this overview, and I think the next generation has got the homework to figure out all of this puzzle and solve all of this question. So thank you very much, Zoltán, for the overview. The next speaker is where is Imre? No, not Imre, Barna. Yeah, yes. You were hiding in there. So Professor Benedikt already was speaking about the magnets, so please give a short overview. Where is the magnet study in Hungary? You have 30 minutes.
Okay, so my talk will be quite technical and easy to digest and illustrated with a lot of pictures. So you can take a mental break, say. Okay, so our team is small but smart, I would say, and consists of young people. So I think this gives us a huge potential. And I will talk about, in general, about the superconducting magnet R&D activity at Wigner, and emphasize how this has been related to collaboration with the FCC project. So this this project was the sushi step. How does it do? Anyway, it's not easy. The sushi septum for the FCC, which was the origin, and all other activities derived from this activity. In particular, it has split off into a niobium titanium superconducting multilayer material R&D project with the University of Miskolc, which will probably continue with novel ideas for niobium titanium cable manufacturing, but I'm not authorized to talk about that because that's on the ideas level and it's probably a kind of industrial secret. And then it is continued also by two...
Átjött ide hozzá.
Hova?
Itt az én monitoromon van, egy kicsit jobbra irányítsa, úgy, igen.
I think, okay. So two European projects which benefited or which actually spinned off from this original activity. One is the HITRI+ EU project, which is dealing with radiotherapy by hadrons, protons or carbon ions. And the iFast European project, where we participate in two activities. And in this talk, I will concentrate on these two activities, because this is our focus right now. And besides these activities, we have provided and we are providing trainings to several of the collaborating partners already. So I think this is a rather fast rising curve. So let me start with the sushi septum project that Michael also talked about in detail. And this was the seed or the genesis to all of these activities. He introduced the FCC. It's about the FCC HH, so the proton machine, which is circulating 8 gigajoule of beams in twice, actually, per beam. And you need to extract this beam very fast, either programmed or in a safety abort, into a dump system that can absorb this extreme energy. I'll try again, last time. Okay, so you start with a kicker magnet that you switch on very quickly. It's very quick, but it only gives a small deviation to the beam, and it starts to diverge from the nominal orbit. And after some distance, it has a large enough deviation so that we can inject it into this septum magnet, somewhere here, which provides zero field for the circulating beam and high field for the extracted beam. And we need a thin wall to make the system compact, yet a high field, at least 3 Tesla, and it needs to be quasi-DC. It needs to follow the beam energy, so it needs to be constantly powered. And yet we want to avoid high power consumption, so we were thinking about a superconducting solution, which seemed to be the only thing. So let me make a first excursion towards the canted cosine theta concept. In this magnet, we superimpose 2 canted solenoids, which have tilted magnetic fields. And if you superimpose them, you have a transverse field as shown, which is what you want in an accelerator. It has a regular and simpler geometry, and it has naturally open aperture for the beam. In reality, this is constructed by machining grooves in a cylinder, and it's an easy and precise process in these days due to the modern CNC machines. And each turn is individually supported. The limit to the performance of these magnets is magnetic forces. So each turn is supported by this mechanical structure, so it's quite robust. So as Michael explained already, this magnet consists of a CCT-like winding, which produces the field. And inside this magnet, we have the blue stuff, which is a passive superconducting shield, which excites eddy currents and expels the field from its interior. So this is the cross-section. You see that on the right-hand side, you have a homogeneous field excited by the magnet, the winding, which is around. And if you cool down the superconductor in zero field and then ramp up the magnet, then the eddy currents automatically expel the field from the inside. The winding geometry was designed such that it gives a homogeneous field in the presence of the shield, which distorts it. And after this idea, we started a collaboration with CERN. to construct a demonstrator prototype. We made proof of concept tests at CERN with an MGB2, an niobium titanium copper multi-layer sheet, and high temperature superconducting tape. And they proved that the concept works. And then the project was a kind of flagship project, which started a new activity at Wigner and also in whole Hungary. It started as a one-man show from scratch in a literally empty room. And we had to construct all the infrastructure for ourselves. And the first test of the magnet was last year, which is a great success. And this was the basis then for serious contributions to several other projects. This is how the magnet is constructed. So you see the two. The red and blue is the two mandrels for the winding, and inside the pink stuff or all the other related stuff is the shield that you insert, and this is inserted in an iron yoke, which boosts the field. So this has been designed at Wigner. And in the collaboration, our partner was CERN, from where we received the continuous help, know-how transfer, sharing of drawings, consultation, and even training. So we could go to CERN and participate in the winding of one of the high luminosity LHC magnets that you see on the right-hand side. This magnet possibly went into the high luminosity LHC. The entire design and construction process was then done at Wigner. And after all, we did some improvements in the design, and this was fed back to CERN. So I think it is a win-win situation that we are really keen on, that it's not a one-way collaboration. So there are a few highlights from this project. On the top left, you see the mandrels, or also called the formers, that were manufactured at CERN. On the right top, that's the winding process, and the experience that we gained was then transferred into the two European projects, and this is how we entered, actually, because we were one of those who had the most experience. And then you add a glass fiber wrap, and this on the bottom center is the completed winding, and the bottom right is the completed magnet. We did some improvements in the design. You see, this is the so-called layer jump, where the cables transition from one layer, one layer to the other one. This was channeled back to CERN, and this is a highlight on the in-magnet soldered joints, which really look like a jungle, but worked quite well. These magnets are typically impregnated with a kind of epoxy resin, but when we were right at that phase, there was a brand new result from Paul Scherrer Institute showing that on short samples, wax, paraffin wax, produced no training. So we made a very quick detour and launched a few months campaign at Wigner to develop this impregnation method with wax to avoid these kind of little holes and voids. The procedure looks like that. It's a schematic figure. It's not that simple in reality. It's a synchronized cooling and heating of the magnet. And this is how it looks like in reality. So it's really cheap and simple. It can be done in-house very quickly. The magnet was shipped to Freya at Uppsala University and tested to nominal current without a single quench. And this is a very fast process because these magnets normally train, which means that you can only reach the nominal current in several steps after several quenches. And that's a lengthy process, and this is at the first trial. Right, nominal. I have a list of different YouTube and other sources, if you want to have a more detailed look. So one of the spin-offs is the material R&D at the Miskolc University. The key component of this magnet is the shield itself. The best candidate was this niobium titanium copper multilayer, which was very expensive, and this was discontinued product, and the experts were retired. So we initiated a collaboration with the university to keep the technology. So this was CERN, Wigner, University of Miskolc, and the ex-engineer from Nippon. Here you see the rolling mill of the university and one of the samples which is being hot rolled at 700 Celsius. The good news is that we could already reproduce the critical current density of the original sheet. And at the same time, we could do this by eliminating one component from the structure, the niobium layer between the two components, which is an unnecessary addition only needed for the technology itself. The contract for the final size sheet manufacturing is in preparation, and here also FCC was the seed, providing a scientific and also commercial demand, and the know-how and the support. Okay. So in the HITRI+, the project is going for heavy ion therapy research and integration. So the goal is to prepare cancer treatment by heavy ion beams. Here I shortly go through it. It's about the design of a curved CCT magnet. And the last activity is the IFAST project, where we participate in the design of a straight CCT magnet. And what is our main focus is now a high-temperature superconductor CCT magnet with 4 Tesla central field, 1 meter. The HTS, the high-temperature superconductor conductor, is a sensitive tape, which has several problems. The tape routing is non-trivial, so you cannot bend it in any way. It needs to be designed, so we developed our own code base for that, and we use a composite cable that needs to be produced in some way. This is the geometry that we designed and optimized. You see the 2 tilted solenoids, and at the 2 ends, maybe another, yes. So we have the soldered joints between the 2 layers, the cables coming from the 2 layers, and we have a very detailed magnetic field simulation that we actually do turn by turn and cable by cable. The CAD design is almost completed. It's quite a sophisticated structure. We transferred the winding geometry from the C++ code to the CAD model, and we already 3D printed a few components to test them. We have a test mandrel that has been manufactured to test, first of all, to practice winding and test whether it can be machined, because it has very thin, half a millimeter, less than half a millimeter thick walls between 25 millimeter deep grooves, which is not that trivial. To machine, we have a solder coating machine under argon atmosphere to keep the solder from oxidation. And we constructed in-house a winding machine that has 2 spools of HTS tapes, copper tapes for stabilization, and on the fly it adds Kapton insulation. And the whole set of spools is on a moving frame that follows the movement of the mandrel, and it's controlled by a Raspberry Pi, so it's a quite cheap and easy system. And that's a little illustration of how the winding can be done. So, okay, let me finish finally. The FCC project created the challenges for us and for many communities. And it was a kind of new project in the sense that it encouraged new concepts and an open mindset. So it was not only a quantitative, but a qualitative change and challenge. So it was explicitly said that please propose something new and not just tune up something existing. It also provided resources and an organized collaboration framework. And the Sushi Septum was a seed project that was very successful, and actually it was kind of ideal collaboration model coming to life, I think. So we started from scratch. We focused on CCT magnet technology, where we can make significant contributions without huge infrastructure that we're lacking. And we are now, I think, quite a significant player in many different projects. And the 3 specific projects are listed below. Right? And finally, let me finish with the acknowledgements. There are a lot of people who contributed significantly, and I'm really grateful to them.
Thank you very much. And as you see, Daniel was speaking about a one-man show, but I think you need a few good young men and women.
Well, now we do, yes.
Okay. Thank you very much. And our last speaker in this section, Gergely Barnaföldi. You have 12 minutes to summarize on the background on IT and detectors. Just speed it up.
I cannot see.
1 minute, yes. So,
okay, until I can start. So thank you very much for the opportunity to make this presentation here. Such as Donny, we joined together to the FCC in the very beginning, and my point is, of course, coming from theoretical physics, but I'm also interested in the topics which are mentioned here. So detectors and novel IT solutions. And there are many, many questions what you can ask after the previous interesting talks. And I would like to point on a few things. Maybe I'm trying to get a bit out of my field, so please apologize if I make any mistakes. So a little bit of motivation. So we have, what is common between pyramids and CERN? So both are visible from the sky, and both has about 10,000 participants to build and construct and design. And recently came out that these were not slaves, but these were really experts living in a city, which was, and they were fully supported with doctors, with churches, with food and everything. They just had to enjoy. So this is pretty much like physicist life, no? And the other important issue that there are a lot of technologies here which was used, and we cannot know anything about that. So the question what I would like to address that, how can we keep up the knowledge what we gained during the LHC and transfer to the FCC, which is much more ahead of us? Okay, so the question one is why? So why we need FCC? So maybe you know very well that CERN and most of the accelerator facilities are running on selling mugs, and the different kinds of mugs you can see here. So the standard model you see here, you can go beyond the standard model, you can search for dark matter, and of course if nothing is enough, you can even go for much more experienced direction to answer everything in one sense. Okay, where and which we have seen nice presentation of the FCC. I don't want to go to the details, but let me mention that there's a competitive one recently presented, the China Electron-Positron Collider, and this is also in the park. Maybe this is just a paper tiger, but maybe it's a real thing, so we have to see on it. So the mankind would like to go to this direction very well, so even at least 2 countries propose something. The when, we have already seen also the plans. So here you see the LHC and high luminosity LHC plans, and here I highlighted the point where we are now. Okay, so we are in the round 3, and we will have the next long shutdown, and then we are reaching the area round 4 and 5. This everything seemingly will end at around 2040. So if I go to a more detailed plan, this is very well scheduled, as you see. So we are starting from here where we are, round 3, and we are ending in 2041. And that's the end of the story of the high luminosity LHC. And that's the point where probably we can start with a circular collider. As you see that there are still work in progress or close to the end at this age, and then we can turn to the operation of this. I can, of course, choose a very beautiful date, the 2042, as a reference for the rest of the talk. But the question is, who will do this job? Because, 2040 is far away. So let's say a little bit about the KSH statistics of Hungarian population, and here you see the working population in the middle. This happened during COVID. There is a little bit of peak. I do not know who was at home and who was not. But anyway, so we have, typically, as in most of the European countries, this is decreasing. But there was a tiny little peak. And let's put where we are now and compare this what we can see in the CERN Gradebook database, which contains all the people who are working for the CERN in some sense. And you see that we are about 111, which means that this is 0.0017% of the working population. So this number I can use as a reference, and I can make further trivial estimations for the future. But first of all, let's go back to the previous era, the Large Electron-Positron Collider. And if you're familiar with the Hungarian H3, you see that this part, okay, here you see the bytes by the Second World War. Here you see the Radko era, when it was forbidden to have abortus. And then the children of the Radko era can be seen also here. Actually, that latter is my age, and that's my family, my father's. If you would jump to 2024, you see that what will happen, that those who are my fathers and mothers are getting out of the working age, and we are doing the same. This is why we are so many here. Thank you very much. Yeah. I hope you enjoy. The question, what will happen later on? And this is the time when we have 111 users. So in 2042, we will have about a little bit less users, and my age will reach almost 65, 70 here. And if I'm going to 2070 to the FCC age, you see that we will be only 75 users. The thing is very flat. Okay, this is estimation for the future, so you don't have to take it seriously, but at least what you see that the possible number of people who can work on the FCC age are pretty much decreasing. So we have to do something. You have to do something. You are here, young people, you have to do something. Another interesting issue that not only who will play the role, but who will pay the role, that's another issue. That here you see that in Hungary, 1.39% of the GDP goes to the R&D activities, 1.14% are the workers are going to the R&D activities, as you see here. Both things are increasing. I mean, from the LHC to the large high luminosity LHC, it was kind of doubled. But still, if you see the capital expenditure and the proportion of innovative enterprises are not changing so much during the ages. So these are all relative values with respect to the GDP. If I put the GDP value, you see that how the GDP was changed during the time of accelerators. Let me remind, there's no interconnection between the two things, so there's no effect of the accelerators, unfortunately, on the Hungarian GDP production. But as you see, everything is going up, up, up. And the big question, what will happen here when I have to ask my crystal ball to make some prediction for the FCC. So that's another issue, but it's very much affected with the number of people who are getting less and less, and of course GDPs per capita. Okay, so the question how we can contribute. So here you see the two stages which we recognize during the participation. So one is the theory, which was presented very nicely by Zoltán Trócsányi. One can connect to the civil engineering, the magnets, of course, Dani presented very nicely, and also the radio frequency capacitor. Actually, in the CRAB radio frequency things has a Hungarian colleagues of ours who are working at CERN. On the other hand, we can also participate once the detectors are ready in the detector design and the detector measurements, of course, the data analysis, of course, machine learning and quantum computing part, and hopefully we can also participate to go to Stockholm. Okay, so what we have did so far. So in the FCC, since the beginning we are there. So my roots are from heavy ion physics, which is very less portion of the FCC in the future. But we were involved to the previously mentioned papers from the heavy ion part. Dani already presented the magnets, and also we have a big interest on simulation ways. We also participated in many outreach activities. We are trying to do something to have more people in the field later, as you could see that we have to improve this, and there's a lot of direction where I put efforts. But how would it look like in the future? Okay, so let's jump to the car, set the 2042, and let's see that how could we contribute to the future. One of the interesting points what Dezső Varga is doing, together with the group and supported by my former student László Olah, is the cosmic muon radiography or cosmic muon tomography, where you can place a detector, which is an applied high energy physics detector, on the ground, and you can say something on the surface, something on the soil between the surface or the rock formations between the surface and the viewing point. So this has presented very nicely in application from speleology, volcanology, civil engineering, and this is the last term which might be used to support a future high-energy physics activities to use this technology either in boreholes or just placing detectors which can not only work in the laboratory but also in a nasty environment. For example, here you see a nice unknown tunnel in the Buddha Castle, taken a picture from a Munich picture underground, like a couple of dozens of meters. Okay. For the future, and to keep in the track the whole local community, we decided to join two large R&D activities of the CERN. The DRD1, which is dedicated to gaseous detector, and this is where DESO is playing a key role. We have long history with large-scale gaseous detectors buildings, and such as the TPC of the ALICE. And we also joined the DRD5, which is quantum sensing and technology, which is associated with the CERN Quantum Technology Initiative, where we participated in the phase 2 and hopefully participate in the phase 2. Just a side remark that the leader of the phase 2 will be our guest for the GPU day, so if you are coming, you can meet her. And they have special interest in quantum network, especially the White Rabbit project, which could be a good project for FCC background. We have connection with the trigger and firmware, and you know very well that the DAQ group, led by Tivadar Kish, is working on DAC systems, not only for ALICE, but for the EDICAM project, for fusion technologies, and also for the CMS. And the recently developed LPGBT plus Versatile plus link is the one which now will be used in the ALICE upgrades, and it was really a unique opportunity to us to continue these activities with further DAQ systems. And we're also trying to looking forward the future. This is the next gen trigger, the new project from CERN, and recently visited us Alberto Di Meglio, who presented and who is the leader of this group, and we're trying to keep up the connection with him. Hardware, the Wigner data center, T0 part was used by the CERN for years. Now we are turning to a new phase, so we joined the Euro, HPC, and the Jena collaborations. Hopefully we will have a supercomputer with 20 petaflops soon, and the Wigner Scientific Computing Laboratory is the one which, with parallel computing, trying to support and speed up the simulations and calculations. Not only that, we have a dedicated site, the Wigner Analysis Facility, which is a specially dedicated site for parallel evaluation of the CERN data, such as the Hyperloop system was first tested here in this site from the ALICE collaboration. Software-wise, I mentioned the parallel computing. So 1 or 2 orders of magnitude larger time takes to simulate an event than to create in the LHC. This will be true also for the FCC. So we joined the HAPMC and the HAPML collaboration in order to speed up the simulation with Monte Carlo, parallel Monte Carlo techniques, or parallel machine learning techniques. And or KID is the HiGene++, which could achieve like 6% faster calculation in parallel way, even for LHC, even for FCC. You see the 100 TV calculation and the interconnection. Of course, there's always things to be tuned, but this is the case. Finally, a similar project. So the machine learning-based hadronization and machine learning-based triggering and image formation. This is related to the Bergen PCT collaboration, the Hadron Therapy project. Here you see a picture with the standard method, and now we are developing with a new student the machine learning version of the same kind, which is a hard, numerically hard and physically hard to solve project to have the proton-based picturing at lower energies. So this is, I think, the point when I reach the summary. So as you see that historically, based on heavy ion physics and the earlier detector R&Ds, we are very well in. We are doing a lot of PR activities to involve more people, but this has to be widened, not only in our community, but involving quantum optics, special materials, as it was proposed very well by the earlier presentations. And the thing that to be in the stakeholders, you have to follow and continue with the upgrade activities, IT, computing, massive parallel computing, and join these new parts of the forthcoming joint projects of CERN, like NextGen, Jena, QTI, FIS2, and so on. And this is where we are in. So thank you very much. And of course, don't forget that where we are.
Thank you very much, Gergely, and also thanks for all of the speakers of this section. And I also appreciate for the Hungarian Academy and the physics department, the physics division to allow this section for this topic. And now I change into Hungarian because a következő szekció will be the CERN 70, and átadom a szót Veres Gábornak, a Részecskefizikai Bizottság elnökének, aki a következő szekciót fogja levezetni. Én azt hiszem, itt most egy néhány perc szünet lesz, és aztán parancsolj. Köszönöm szépen a résztvevőknek, hogy meghallgatták ezeket az előadásokat. Az előadónk megy vissza dolgozni, viszont Barna Dani, Gergely és Tepsen Zoltán, Trócsányi Zoltán továbbra is itt marad Magyarországon. Akit érdekel, az megtalálhatja őket a továbbiakban. Köszönöm szépen a részvételeteket.